Hello viewers, welcome to this next lecture of our series of lectures on solid state. In today's lecture, I will talk about the structures of some crystalline solids. This we will try to build on what we have done earlier in earlier sessions. Today's session has been planned as follows. That is, to begin with, I will try to quickly review what we did in the previous session. Thereafter, I spent a lot of time on analyzing the CCP unit cells. Because we have shown earlier that they happens to be equivalent to FCC lattice. Thereafter, in this process we will try to see that where are the locations of tetrahedral and octahedral voids in our CCP unit cells or FCC unit cells. Thereafter, on the basis of all this, we will try to learn about the structures of some metallic solids. Thereafter, we will pick up that of the crystal structures of some alloys. This will be followed by structures of some ionic solids. That is very important area which we are going to touch upon, and towards the end we will try to sum up what we do today. So, we make a beginning by recalling what we did in the previous session. In the previous session, we made a case for why to talk about closed packed structures. This was thereafter logically followed by discussion on closed packed structures in 2 dimension and in 3 dimension. And in the process, we learnt about different kinds of voids, trigonal void, tetrahedral voids and octahedral voids. Thereafter, we talked about that when you do closed packed structures in the 3rd dimension, then we come across 2 kind of packed structures, that is called as the AB-AB repeat and ABC-ABC repeat. And in both the cases, we saw what kind of unit cells are there. So, with this as a background, let us pick up our threads and get going from what we did in the previous session. We showed that CCP, that is ABC-ABC repeat, is equivalent to FCC. So, from this starting point, we will try to analyze this structure little further, because we find that you will recall that when we talked about closed packing in 3 dimensions, we came across different kind of voids and all. Now, let us try to now figure out where are these voids into a unit cell. So, to move further, what we do is we take up an analysis, a detailed analysis of our FCC unit cell. To do that, let us try to again recall our FCC unit cell. You remember that to create FCC unit cell, what we did was that we took CCP, that is cubic closed packing structure, and from there we picked up 14 elements selectively. 1 of first layer, that is the A layer, 6 of B layer, another 6 of C layer, and 1 of the A layer again, and put them together. That means this is my first layer, this is 3, 2, 1, and this is 3, 2, 1, and this is the 4th one. And put together, that gives me, if I clean up the structure, I get a very familiar FCC unit cell. Now, what we do is, basically my objective is to locate where are the tetrahedral voids and how many of them are there, where are the octahedral voids and where are they located. To do that, what I suggest here is that we take the small cube, that FCC unit cell, and divide it into 8 small cubicles. That is, we cut through all the 3 dimensions there, cut it to half in all the 3 dimensions. What I get is 8 small cubicles. Having done that, what we do is we begin by picking up just 2 of those 8 small cubicles. I have purposely picked up, say, this small cubicle here. So, this is out of the 8 cubicles, this is my front left bottom cubicle, and that is my back right top cubicles. I have taken out of the 8 cubicles, I have taken 2 small cubicles here, and in the center of each one of them, this red mark here, red sphere here is indicating a tetrahedral void. Now, how is it a tetrahedral void? You just see that there is one atom of layer A, and then this is in touch with 3 atoms of layer B. That means these will be 3 face centers. Okay. So, that will form a tetrahedral void. Similarly, here also this is a corner atom here, and then there are 3 face centers. That means the face center here, top, back one and left one, the right one, this will make a tetrahedral void here. So, that means just there are two depictive ones. If you really look into that, that is behind every corner atom there is a tetrahedral void. Let us see it with the help of a model now. Now, you will recall that we had a model of our CCP 1661 giving me an FCC unit cell. Now, if I look at it, say I pick up any of the carbon corner atom, say I take up this corner atom, you just see behind this corner atom there are 1, 2, 3 atoms of the previous layer, and these 3 atoms are essentially, you can see that this is the phase center of the front face, phase center of the top face, phase center of the left face from your side. Okay. So, that there is a tetrahedral void. You can see from any dimension this is a tetrahedral void, this is a tetrahedral void here. So, I have chosen this corner, you take this corner now. Here again I find that there are 3 atoms behind it. So, this is the phase center, another phase center. Irrespective of which corner I choose, I will come across 3 atoms just behind it. So, that means just behind every corner atom there is a tetrahedral void, and since there are 8 corner atoms in a cubical unit cell, there are 8 tetrahedral voids in FCC lattice. And now, if you really look further, if I just look into, say, start from here, go through and then talk about the body diagonal here, that means from the top end of this, the bottom end of the back side here. So, you just see if you pass through and through, my tetrahedral voids will be located at 1/4 the distance of this body diagonal there. So, there are 4 such body diagonals. So, each one of them at 1/4 there will be tetrahedral voids. So, there are total of 8 tetrahedral voids located into one unit cell of FCC. Okay. So, that is a very, very important number for us, because that has a lot of significance. We will come to that as we proceed. So, there are total of 8 tetrahedral voids. This picture shows them clearly. The white spheres here are the tetrahedral voids. So, they are also shown into small tetrahedras here. So, this is a different kind of representation. So, this is one tetrahedral and so on and so forth. There are 8 small tetrahedras there. That means, in each small cubicle there is a tetrahedral void. Now, if you look little further, as I just mentioned, the tetrahedral holes are at 1/4 of the body diagonal. If you look little closely, we find that there are these the tetrahedral voids are of 2 types. Let us understand that. The tetrahedral voids of type shown here, right here, it is called as a T minus void. Why is it T minus? Let us understand. Now, I have been telling that this is my A layer, this is the B layer, this is my C layer, this is another A layer here. So, this tetrahedral void is formed by 3 atoms of B layer, and the solitary atom here, the 4th atom, happens to be of the preceding layer. So, it is preceding layer, it is T minus. In this case, 3 atoms belong to my C layer and 1 atom is of the next layer, succeeding layer. So, it is T plus. So, there are 2 types of voids there. There are T minus void, there are T plus voids. And if we analyze each one of them, all the 8 of them, we find that there are 4 of T minus type of voids, 4 are T plus type of voids. This is very, very important, because, and if you go further into this, we find that if this is T minus, the tetrahedral void next to that will be T plus, next will be T minus, then there will be T plus, and so on and so forth. That means, 2 neighboring voids will be of different kinds. This will become very, very pertinent when we talk about structures like, say, zinc sulfide and many things. Okay. So, this is very, very important to understand that there are 2 types of tetrahedral voids, T minus and T plus, and both of them are 4 each. The total happens to be 8. Okay. Now, let us move on to the octahedral voids. Here again we find that there are 2 types of octahedral voids. Let us understand them. The first one, type 1, is located right in the center of the cube here. Now, what you see is that this atom here right in the center, because this is not an atom here, this is a space, a void, which is shown with a different color here. Now, this void is created by 3 atoms of B layer and 3 atoms of C layer, and they will be in the direction in the opposite sense. You know that the B layer is, you have taken 3, 2, 1, this is 1, 2, 3 and so otherwise. So, these two will be, there will be two trigonal voids which are overlapping each other in the opposite sense. So, this is going to be my octahedral void right in the center. Again, let us see it with the help of the model now. Now, in the model what we see is that what I am referring to here, this is my CCP structure or FCC structure. Look at, you start from anywhere. So, this corner I am talking about. So, there are 3 atoms right here. Okay. These 3 atoms of, this is my A layer, B layer, C layer and then A layer. Take these 3 atoms of my B layer and there will be 3 atoms of the C layer in sense opposite to that of the A layer, B layer. So, right in the center of the 2 there will be a octahedral void. That means, octahedral void of type 1 is, there is only one of these kinds and that is located in the center of the cube. That is one octahedral void. That means, this octahedral void of type 1 is 1 per unit cell. Okay. Let us move further, because there are many more octahedral voids there. This is just the same thing which I just showed with the help of model here. So, you see that this void is created by 6 face center atoms. So, 3 coming from my layer B and 3 from layer C. You can see that they are in the opposite sense. So, this is pointing downwards, this is pointing upwards. So, that is where the octahedral void comes into. So, that is the kind of picture we have seen earlier about the creation of octahedral void. And since in octahedral void, this void is in touch with 6 neighbors here, 3 here and 3 here. So, this will have a coordination number of 6, which means that anything which occupies this void will have a coordination number of 6. We will come to that as we proceed further. Now, besides this octahedral voids of type 1 are very simple to understand. The second type of voids, what is called as type 2, they are slightly tricky to locate. So, what you see is they are located at the center of the edge. I will try to show one here. So, this is my the central cube here is my reference point. So, what I try to show here is that this atom here, this is actually a void. This void here is the edge center here. What you find is that this void has 6 neighbors again. One neighbor is, the 2 neighbors are the corners of the same edge, fine. Then this face center, the top face center and the right face center, 4, that means 2 here and 2 here, they have 4 atoms now. And then of this neighboring unit cell, so this face center here and this face center here. So, these 3 atoms here and these 3 atoms here generate what is called as an octahedral void here, because we are talking about a 3-dimensional lattice. So, if I look at one of the unit cells, this unit cell is in neighborhood having similar kind of unit cell all around here. So, if I look at closely, we find that this place here, that means the center of the edge actually is the location of an octahedral void. Let us have an alternative representation of the same thing. Here I have shown 2 such things here, that means this is one octahedral void here. So, there are these black dots represent the FCC in question and these blue ones are the contribution from the neighboring unit cells here. So, here also there are 2 are coming from the neighboring unit cell. So, these green dots here are the octahedral voids. I have just shown 2 representative ones. Since there are 12, because this is a uniform symmetrical structure, since there are total of 12 edges of the cube, so there are 12 such octahedral voids. So, we find is that in our octahedral void, in our CCP structure, there is octahedral void of type 1, there is just one in the center of the cube, and at center, that is a type 2, there are 12 such things. And now, another important thing here is that in such a cubical arrangement here, each edge is shared by 4 unit cells. That means, suppose I got one unit cell here, second one, third one and the fourth one. So, this edge is shared by 4 unit cells. That means, any void here which is in the edge center will be contributing to 4 different unit cells. That means, in other words, the contribution to a given unit cell is just 1/4 of that. So, there are 12 such octahedral voids, each contributing 1/4. That means, 12 into 1/4 makes it 3. That means, the total contribution of the octahedral voids of type 2 to the unit cell adds to 3. So, there is 1 of type 1 and 3 of type 2 put together, there are a total of 4 octahedral voids. That is again very important. So, what we see from this little analysis, that cubic close packing, each lattice point or the atom has a coordination number of 12, we have seen that earlier, and also 74% of the space is occupied, that also we have seen earlier, and then the interstitial sites or the voids are, octahedral void is 1 per sphere. I will explain how does it come out to be 1 per sphere, and tetrahedral voids are 2 per sphere. Now, these numbers come here, what we have just seen is that there are 4 octahedral voids per unit cell and there are 8 tetrahedral void per unit cell. But also we know that in case of FCC unit cell, there are 4 lattice points per unit cell. So, since there are 4 octahedral voids per unit cell, there are 4 lattice points or 4 spheres per unit cell. So, there is 1 octahedral void per sphere. Similarly, since there are 8 tetrahedral voids in 4 spheres of the unit cell, so there are 2 tetrahedral voids per sphere. So, that is a kind of feature we have about the cubic close packed structure or FCC lattices. Okay. So, what we have done so far is we have done an analysis and realized that in case of an FCC lattice, there are 2 types of voids, octahedral 4 of them, tetrahedral 8 of them, octahedral located in the center of the cube 1 and on all the edges 1 each, shared by 4 cubes, and tetrahedral voids right behind each corner there is 1 tetrahedral void. So, there are a total of 8 of them. Okay. Now, with this as the background, we are now equipped to take up an understanding of structure of different kind of crystalline solids. That is the main theme of our this session today. Now, we start with metallic solids, were simplest ones, because we know that metallic bonding is a non-directional bonding, and in metallic bonds or metallic systems, we can expect the metal ions to be crystallizing in one of the close packed structures, because as per the electron C model, there is a ordered arrangement of the metal ions in the sea of electrons. So, we expect this to be packed into some kind of an ordered structure, and typically they are expected to be in close packed structures. And what we find is that all the 3 kinds of cubic structures are observed. Simple cubic, polonium is an example which crystallizes in simple cubic form, and there are a number of like alkali metals, vanadium, chromium, molybdenum, tungsten, iron, they all give body centered cubic structures, whereas nickel, copper, silver, gold, aluminum and lead, they all give face centered cubic. So, that is the kind of structures we have, and these structures can be rationalized in terms of our close packed structures. So, what we have been focusing on are FCC, that means all these are the examples whose structures can be rationalized in terms of what we just discussed as CCP, ABC, ABC, repeat. Okay. Now, let us move on further. Let us talk about the structure of some covalent network solids. Now, in case of covalent network solids, the covalent solids typically we have seen the examples earlier, the diamond, graphite, etc. We find that in these cases the constituent species, the atoms per se, are linked together by very strong covalent bonds, and they are highly directional. So, in this case what happens is that is the kind of structures we have for diamond and graphite. Then we can take up the structures of some alloys, and in case of alloys we find there are 2 types. One are called as substitutional alloy. In this case what happens is, so you have a metal and there are different metal atoms which are quickly nicely packed together, and what happens is some of these atoms of the host metal are lost and they are replaced by atoms of a different material but of similar size. Say example is brass. And second kind is interstitial alloy. In this case what happens is that the host element or the metal has got nice packed structure, and there are small voids, interstitial spaces, wherein the guest kind of atoms come and sit over there, and the typical example is your steel. So, this is brass. So, in brass what is happening is the atoms of copper are replaced by that of zinc. They have a similar size. So, that gives a substitutional alloy, whereas in case of steel this is iron packed together fairly well, and then wherever the small voids are there, small carbon atoms get into that and they give rise to what is called as a interstitial alloy. Now, with this quick reference to different kind of structures, we move on to structure of ionic solids. That is what we want to really spend time on. In general, the description of ionic solids or ionic crystals is not very straightforward, because in case of metal and all, there are only one kind of entities, they pack together. But in case of ionic solids, what happens is that they are very complicated, because we have to ascribe the position to all the cations as well as the anions. So, we need to specify two kinds of positions. So, it becomes a little complicated, and the analysis of FCC unit cell, which we have taken up earlier some time back, that becomes very handy in understanding the structure of some simple ionic solids. And let us take some ionic solids now. We will begin with the simplest possible solid which we come across so very regularly, that is sodium chloride. Now, with I will request you to recall what we just learnt about our CCP or FCC lattice. If you can recall that how many tetrahedral voids and where are they, how many octahedral voids and where are they. So, if you can just keep that mental picture with you, then talking about structure becomes very, very simple. Let us see that. Now, to describe structure of sodium chloride, what we have to do is, we just say that is the chloride ions are forming FCC, that is a CCP structure, and sodium ions are in the octahedral voids, or the reverse of it. But normally the first written here, the chloride ions, because a larger ion will form CCP and the smaller ions I will get into the octahedral voids. With these two statements, I have described the structure fully. Let us understand how. So, what we do is, this is my, you see that black spheres here, if you just ignore for a moment these green dots here. So, this black spheres is, we have familiar picture now, that is my FCC or CCP structure, and wherever there is an octahedral void, one in the center of the cube and all edge centers, wherever there is an octahedral void, so we just put one sodium ion, that these green spheres now are my sodium ions which are smaller in size. Put that there, my structure is there. It is as simple as this, because we have analyzed the structure. Now, just making these two statements, that chloride ions form CCP and sodium ions are in the octahedral voids, I have described the structure. I do not have to really mug up the structure, I can create it myself. I analyze it a little further. Say the number of chloride ions will be the number of lattice points per unit cell, and we know that there are 4 unit cells, 4 lattice points per unit cell for FCC. Number of sodium ions, that is the number of octahedral voids, and that happens to be 4. That is why I just rationalized that earlier, because that analysis is becoming very handy now. So, that means if I just look at this small structure which we made here, that this nothing but that represents Na4Cl4. That means, in this structure shown here, there are 4 of sodium ions and there are 4 of chloride ions there. That means, there are 4 formula units per unit cell in case of sodium chloride structure. That is so very simple to rationalize, having understood our few fundamental things, that CCP is FCC and CCP has 4 octahedral voids, 1 of type 1, 3 of type 2, and there are 8 tetrahedral voids. So, having done that, we are very comfortable in talking about structure of some of the simplest solids. Let us move further. So, this is a different representation of same structure. Now, let us talk about zinc blende or zinc sulphide structure, because zinc sulphide exists in 2 forms. One is zinc blende, one is woodsite, which actually is based on HCP, which we do not want to touch upon. We will just continue with our zinc blende structure, which is based on our CCP. So, again I need to make only 2 statements. Sulphide ions, the larger ones, form CCP structure, and zinc ions are in the alternate TH holes, that is tetrahedral holes or voids. That means, in this case either T plus or T minus are occupied. Let us see that. So, what you do is, this larger size yellow balls here, yellow spheres here are the CCP FCC structure made up of sulphide ions, and out of the 8 tetrahedral void, 4 are occupied. So, this is my T minus, this is T minus, this is T minus, this is T minus. So, I have occupied T minus in this case, that is my zinc sulphide. I do not have to bother about it, I just have to make 2 statements, that which ion is making CCP and where are the other ions located. Again, let us go further. As we did in case of sodium chloride, here also we know that there are 4 lattice points per unit cell and there are 4 zinc ions. So, 4 sulfide ions, 4 zinc ions. So, it is again incidentally Zn4 S4, again 4 formula units per unit cell. So, that is the kind of structure we have here for zinc sulfide, slightly more clarified structure, same picture. Let us move further. Talk about calcium fluoride or fluoride structure as it is called. Again, I have to make only 2 statements, that is the calcium ions are forming CCP and fluoride ions are in the tetrahedral holes or the voids. Then my structure is understood. You can on your own also draw this structure. What do? We will form first the CCP, the blue balls here, and they are basically representing the calcium ions there. And wherever there are tetrahedral voids, we know that there are 8 of them. So, that will be the fluoride ions there. So, that is my structure of calcium fluoride. It is as simple as this. Let us go a little further. Number of calcium ions is same as number of lattice points, that is 4. Number of fluoride ions same as number of tetrahedral voids, again happens to be 8. So, that means my formula will be Ca4F8, or in other words it is CaF2, that is what my calcium fluoride is. So, you see that how simplified has it become to talk about structure of ionic solids, because otherwise in the absence of this kind of analysis it becomes very difficult to remember the structure, because okay, they look very complicated, but having understood what is where, we are in a very comfortable position to talk about the structures. Let me take one more example, say of antifluoride or lithium oxide or sodium oxide. In this case again I need to make only 2 statements. Oxide ions are forming CCP sites and lithium ions or sodium ions are in the tetrahedral holes. It is just like this, my structure is done. So, I make an FCC lattice, and wherever that lattice points are there, I put my oxide ions, which are shown by blue balls in this case, and wherever there are tetrahedral holes, I just put my lithium ion or sodium ions. So, that gives me the structure of antifluoride. Similar analysis again. So, there are 4 of oxide ions and there are 8 of lithium or sodium ions, and again this becomes Li8O4, in other words it is lithium oxide. So, that is the positioning of cations and anions, it is reversed from the fluoride structure. In calcium fluoride it was the other way around. In case of calcium fluoride, what we had was, we had calcium ions forming CCP and fluoride was inside as tetrahedral holes. In antifluoride, that is why the name is antifluoride, because there is a reversal of location. So, that is one more structure is understood. Move further, we can even talk about diamond structure. We did talk about it earlier, we referred to it earlier, because we can rationalize that in terms of CCP again. So, what we see is all CCP sites and alternating TH, that is tetrahedral voids, are occupied by carbon atoms which are linked together by covalent linkages. So, that is the kind of structure we have, that is a diamond structure. So, because all CCP sites are carbon, and wherever there are that is alternative, that is either T plus or T minus tetrahedral voids, there are carbon atoms which are linked together through covalent linkages, and what you get is the structure of diamond. Let us move on to cesium chloride. Most of the people make mistake in talking about cesium chloride. If you ask anybody what is the structure of cesium chloride, they will say it is BCC. Please stand corrected, it is not BCC structure, it is BCC type structure. I will explain that. Basically what happens is, that is the structure of CCP, the unit cell of cesium chloride. What you have is, you have chloride ions forming a simple cube. It is not FCC structure, it is a simple cubic structure, and in the so called body centered position there is a cesium ion here. So, this is cesium ion and the yellow ones are the chloride ions here. Now, this would have been called as a BCC structure if even here also we had a similar atom or ion, which is not. So, it is not a BCC structure, it looks like BCC, so we call it as BCC type structure. In fact, this is a simple cubic structure, let us understand that. So, if I look at say I make 8 small unit cells of cesium chloride, that means all these small cubicles which I have worked out earlier. So, they happen to be chloride ions and the centers of each one of them happens to be cesium ions. So, if I link all the cesium ions together, we find that they also form a simple cube. So, basically what happens is, cesium chloride actually can be best represented as interpenetrating simple cubes. That means, there is a cube of chloride ions, this is a cube of cesium ions. The two are interpenetrating, that is a kind of structure, but deceptively it looks like a BCC kind of structure. It is not BCC structure. Please be very clear about it. It is a interpenetrating simple cubic structure. After talking about all these ionic structures, let us move further and talk about some more interesting structures here. C60, that fullerene we all are familiar with. Even fullerene, when it, because this is a large molecule of C60 which crystallizes in the form of our familiar FCC lattice, that is how it is formed. That is something interesting observation I thought of sharing with you. So, besides fullerene, there is another very interesting structure which will be you will be interested in knowing, that is foot and mouth virus. That virus actually crystallizes in form of BCC structure. That means, this is a virus shown here, and the virus when it crystallizes, that forms a BCC kind of a structure there. It is very interesting observation, just a thought of sharing with you in the context of crystalline materials. It is not a crystalline material, but that is how the structure comes up. Okay. So, let us quickly sum up what we done today. What we done today is, we have quickly reviewed briefly the contents of the previous session. Thereafter, we performed a detailed analysis, a very pertinent analysis of CCP unit cells in terms of the location and number of tetrahedral and octahedral voids. Thereafter, we described the structures of some metallic solids, alloys and network solids, and this was followed by analysis in detail structure of some of the simple ionic solids, and we realized in the process that the analysis of CCP structure becomes very handy in communicating the structures of ionic solids. So, with this we come to completion of one aspect of our understanding of solid state, a descriptive part of it. In the next session, we will like to take up the symmetry aspect. So, what we will do is, we actually have to talk about the crystal symmetry, but to make case for that, to make understanding easier, we will start with understanding of molecular symmetry to begin with, and then we will see how do we extend our